Okay, we're going to start this video by looking at the units of impedance, and I wrote down the three equations we came up with in the previous video for impedance of a resistor is just equal to resistance, impedance of a capacitor is minus J1 over omega C, and impedance of an inductor is J omega L. Well, we know from DC that resistance just has units of ohms, so impedance of a resistor, since it's just equal to resistance, has units of ohms. But now let's look at the units of the impedance of the capacitor. And to do so, we're just looking at the magnitude, okay, 1 over omega C. J isn't part of this because J is the theta. So what we have here, unit-wise, is that you have omega, which has units of radians per second. And then you have capacitance that has units of farads, which is equal to Coulomb per volt, so charge per volt. And radians is a dimensionless quantity like degrees, so it doesn't really come into play here. So what you have, or what you end up with, is that you have charge per time, which is current, divided by volts, and it's 1 over that. So it comes out to the units of the impedance of a capacitor is volt per amp, which is an ohm. So you see impedance of a capacitor, just like impedance of a resistor, and just like resistance in DC circuits have units of ohms. Now let's look at the units of an impedance of an inductor, and again, we're not including the J, we're just looking at omega L. So you have radians per second again for omega. Okay, where radians is dimensionless, and that's times inductance, which is henries, which is magnetic flux divided by current, and then rate of change in magnetic flux, that's Faraday's law, that's voltage. So you see again, you end up with units of volt per amp, which is equal to ohms. So impedance in AC circuits, just like resistance in DC circuits, has units of ohms, and this may not seem that big of a deal, but what this means is that I treat, or we can treat, impedance just like resistance. And what I mean by this is that in DC circuits, when we had resistors in series, we would just add them up to get the REQ. And when we had resistors in parallel, we could do sum of reciprocals reciprocated to get REQ, or if we had two resistors in parallel, we could do product over sum. Well, I can do the same things with impedance. So impedance is in series, to get ZEQ, I just add them up. If they're in parallel, I can do sum of reciprocals reciprocated, just like I do with resistance. And if I have two impedances in parallel, I can do product over sum. So, as a couple of examples, let's say we had a non-ideal inductor, and this is a representation that we often use for a non-ideal inductor, where we include the resistance of the winding that makes up the inductor as a separate resistor. So, you know, here's the inductive part here, and then often the resistance of the inductor is labeled RL, where L here is inductor, not load like it was in Thevenin circuits or equivalent circuits. So this is resistance of the inductor. And just making up some numbers here, let's say that, you know, in the particular circuit, this non-ideal inductor is connected to, you know, let's say the source frequency and the L just happened to give us a value of 6, so that the impedance of the inductor was plus J 6 ohms. And let's say the resistive part was 10 ohms. Okay, well, to get Z equivalent of this non-ideal inductor, I would just add up these two impedances, and I end up with a complex number of 10 plus J 6 ohms. Okay, so you see I just add up the impedances just like I would add up series resistances in DC circuits. The difference being in DC circuits where the resistors are just scalars, you know, I'd get a scalar quantity, but here if you have an impedance that has an imaginary component to it, and you add it to a resistor which has is purely real, well, together they're going to give you a complex number, as you see here. All right, here's another example, this time a non-ideal capacitor, which is often shown as a parallel circuit like you see here. This resistance actually represents the resistance of the dielectric between the plates of the capacitor, which is usually high. So, you know, let's say it's 10,000 ohms. And then let's say the minus J 1 over omega C in the particular circuit that this capacitor is hooked up into, let's say it comes out to minus J 300 ohms. Alright, well, to get the ZEQ, I could do product over sum, where I'd have the 10,000, and I'll just write it as 10K, times the impedance of the capacitor, the minus J 300, and then that would be over the sum, so I'd have 10K minus J 300. Okay, so again, this is where complex math, being able to do complex math is important, because you'd have to multiply this out and then divide. And if you do so correctly, I'm just going to give you the answer here. This is actually good practice for you to do on your own to make sure that you can do this, that you should get approximately, in polar form, you should approximately get, let's see here, make the approximate symbol. Well, again, not cooperating here. So approximate, okay, there we go, approximate sign. You should approximately get a magnitude of 300 and an angle of minus 88 degree ohms in polar form. In rectangular form, this has a real part of about 10.5 ohms and an imaginary part of 299.8. You can see because of this angle so close to minus 90 that you're going to get an imaginary part close to the magnitude here. So either of those two answers would be acceptable. Okay, so again, you might want to do that example on your own just to get some added practice. All right. Now, also a couple of important things here, and once we're done with this, these topics here, we'll be able to start doing some AC analysis problems. But I just wanted to point out that in general, impedance is a complex number, because in general you'll have resistance along with the imaginary part that comes from the storage element. Remember, the inductor gives you the plus J imaginary part, and capacitor gives you a minus J imaginary part. Resistance always gives you the real part of the impedance. And this number for the imaginary component, we often will label X, which stands for reactance. Okay. So you see we have reactance of an inductor, and it's just omega L, and reactance of a capacitor, which is 1 over omega C. So reactance is just magnitude of impedance. Reactance is impedance without the J, without the phase angle, right? Because remember, impedance of an inductor is J omega L, and impedance of a capacitor is minus J 1 over omega C. So for reactance, we're just taking the magnitudes. There's no such thing as reactance of a resistor, because again, the resistance gives you the real part, and reactance has to do with the imaginary part of the impedance. The last thing here, before we move on to some AC problems, AC circuit problems, is I just want to talk about what the significance of theta Z is. So, you know, theta Z for a resistor, just to remind you, right, for resistor, theta Z was 0 degrees. For a capacitor, theta Z was minus 90 degrees. and for an inductor, theta Z was plus 90 degrees. All right. Well, theta Z gives you the angle between the voltage and the current, because if you just use your knowledge of complex math, if you have a complex quantity, which impedance is, equal to a ratio where both of these are complex quantities, right? In sinusoidal voltage, sinusoidal current, they're both, when represented as a phasor, a complex quantity. They have a magnitude and an angle. Well, to get the resultant angle, theta Z, it would just be the numerator angle, theta V, minus the denominator angle, theta I. So you see, theta Z is just the difference between the angles of the voltage and the current for that impedance. So some pictorial representations of this I have on this handout here, where here is a phasor diagram, and don't let the term phasor diagram throw you. Remember, phasors are just like vectors. They have magnitudes and angles, so if you're more comfortable thinking this as a vector diagram, that's perfectly okay, because it's essentially the same thing. So this shows the phasor diagram for a voltage across a resistor and a current through a resistor. And since theta Z equals 0 degrees for a resistor, that means the difference in angle between the voltage and current for that resistor is the same, that there is no difference, and that's why you see both phasors at the same angle right on top of each other. So that's a phasor representation. Here's a time representation where if current is cosine, well, the voltage across the resistor will also be cosine because they're in phase, they're in step. There isn't any phase difference between the two waveforms, the voltage and current for that resistor. Now for a capacitor, there's a 90-degree angle between its current and its voltage. So in the phasor diagram, you can see here's our 90-degree angle, and also these phasors are rotating in this plane counterclockwise, both at the same frequency. Okay, the current and the voltage are rotating counterclockwise, and they're rotating at the same rate, so this 90-degree angle is maintained as the phasors rotate. And since the phasors are rotating counterclockwise, we say either that the current is leading the voltage or the voltage is lagging the current by 90 degrees for a capacitor. Okay, so either the current is leading the voltage by 90 or the voltage is lagging the current by 90 for a capacitor. And then this shows in time what it would look like, that if current is cosine, well then the voltage for the capacitor would be sine. And as you know, there's a 90-degree difference between sine and cosine. Well, the inductor is the opposite case from the capacitor, where the voltage leads the current by 90 degrees or the current lags the voltage by 90 degrees. And then it's just the opposite here, where if you have cosine for your current, you'd have minus sine for your voltage for the inductor. Now, theta Z being the difference between the voltage and current angles is true whether you have pure resistance or pure capacitance or pure inductance, or you have a combination of these. So for example, if you had a non-ideal inductor, let's say, where both the resistive part and the inductive part had the same value, so let's say the resistive part was 5 ohms and the inductive part was plus J 5 ohms. Well, Z equivalent would be 5 plus J 5, and you see the theta Z here would be 45 degrees. So here, if we go back to my handout, so here, and again looking at the inductor, where the theta Z is 45 degrees, that means that this voltage across that non-ideal inductor would be leading its current by 45 degrees instead of 90. Okay, or likewise, the current would be lagging the voltage by 45 degrees. So theta Z being the angle between the voltage and current for an impedance is true no matter whether the impedance is a pure amount of resistance, capacitance, or inductance, or if it's a combination of any of these three. Alright, well that's all the preliminary information we need to know, and the next couple of videos will be AC circuit problems where we're utilizing all these concepts we learned as far as phasors and impedance, and also using complex math that we've learned.